Hello and welcome to my second physics lab, the motion of a falling object. So first, to understand the motion of a falling object, we need to understand some key concepts. The most important one here is gravitation, and that is given by the force equals the gravitational constant times the first mass, the second mass, and the distance between them squared. So near Earth's surface, the force due to gravity on a given object is going to be equal to negative mg, this being because it is falling in the negative direction, the mass of the object, and the acceleration due to gravity, which is approximately 9.8 meters per second squared. This is given by the standard variable values of the gravitational constant, the mass of the Earth, and the distance between the center of the Earth and the object that you are dropping, approximately. We'll also need to understand Newton's second law, which is essentially that the acceleration of an object increases as the net force increases. That's all you really need to know. There is no difference between the change in momentum, the velocity update, and the position update in this experiment compared to other motion experiments. However, we need to understand the drag force in this equation, and that is going to be equal to the force of drag equals this constant here, which is essentially determined by the shape of the object, times the magnitude of the speed squared. So the purpose of our experiment is to show the motion of an object as it falls from rest of a specific height. And we want to demonstrate essentially that this falling is going to be more accurately described by a model with drag than without one. And we're going to do this by comparing two computational models, one for each, and assuming that it's only falling in the y-axis. So here, the system is just the rag. I represented it with a ball. It's not a ball. That's okay. First, we have the rag without drag, as we would expect it just with the force of gravity, and with drag, which is going to be increasing as the speed increases. So let's go over to the tracker analysis. Here you can see it falls in small amounts and then large amounts as it goes on. You can see this curve right here. Lots of data. And you can essentially observe here gravity influencing the speed changing over time. There we go. So we have a frame rate, and that's going to be influencing the position and any of the time, any of the numbers here. This is the size of the rag, which is important to determining essentially that constant. The mass of the rag, its initial time, position, velocity, final. And the velocity should be zero because we're dropping it from a height and rather than throwing it down or something like that. So the first computational model that we're going to be observing is this, which uses this standard velocity and position update formula. Here we have the net force divided by the rag's mass times the change in time. And here, that velocity from here times the change in time again. You can see it represented with all of the given values in this equation here. I can also run it. As you can see, it falls approximately according to how we saw in the tracker with the velocity, the speed changing over time. It is not constant. You can also see the direction of force. And here's those results. Now we can go to the computational model without drag. So here, it's essentially the same for position, except that this net force is now given here by the force of gravity plus the drag. The force of gravity is going to be as we determined, which is the vector here minus mg. And here it's going to be according to this in the function. The force of drag, that b times, this should be absolute value of the speed squared. You would then put this in like so, as you can see here in the code, essentially define how much drag is going to be pushing the rag up in a sense. Again, show this. You can see that the position does not change quite according to what we saw in the last one, and that the velocity actually isn't a straight line anymore. It's getting smaller as it goes on because that drag force is increasing, which you can see up here. Here's those results again. Now comparing the estimated observed position of the rag in the different models, you can see that the second model here in blue and the actual tracked models are fairly similar until we get to the end. And that is because drag is actually being taken into account as it goes on. Whereas with no drag, it's assumed to be falling a lot faster, which you can see represented here, the drag force gradually increasing over time there. At the beginning of the experiment, the observed and stimulated graphs are largely similar, and then around 0.3 seconds, as we saw, the air resistance did have an effect, making them diverge. The model which incorporates friction is therefore much more accurate. Errors in this include the tracker, object not adhering perfectly to the one-dimensional model, tumbling, all that stuff. As well as that, the coefficient for proportionality constant, I got it essentially just from a square falling. And the rag, I mean, it should be behaving like that, but it's not perfectly accurate. So discussion questions, what does it mean? Which model predicts a terminal velocity? So to find the terminal velocity, you essentially go to this point here where the speed begins to not change. And that's because the force of gravity and the drag force are making themselves equal to each other. So the net force is going to be closer to zero. And that's where that air resistance is really going to come into effect. And we can see that as it gets closer to the floor at greater speeds. So when thrown down, would the terminal velocity be the same? Absolutely. The force of gravity does not change because the mass of the object does not change. Therefore, the terminal velocity would be exactly the same. It would just start essentially later in the simulation. It would look like as if it had started here with that extra speed, and then that speed would quickly have an effect on the magnitude of the net force.